Hi, today we're gonna solve two challenges from 35C3 CTF, which are Arraymaster 1 and 2. These challenges are exactly the same, except for the fact that the first one includes a function which directly pops a shell for you to aid during the exploration phase. We're gonna solve directly the second version, so our exploit will work for both. Since the focus of the video is exploit development, I'm gonna work directly on C code rather than binary. So let me show you. The code is pretty small, not too much lines. Let's give a quick look to the main function to get an overview of what the program does. As you can see, it handles arrays essentially. So you can create arrays with the IDs, a type, and the length. Then you can list these arrays, delete them, set the value of their elements, and get the value of the elements. And then the main takes care of prompting the menu with the different options and reading the input and calling the relative function. So we can go back to the type definition. Here we can see the array structure as 5 fields, a length, a type, both of type size t. Then we have a pointer to a backing store buffer, and finally we have two function pointers which are get and set, and we can see just immediately after that we have different implementations of the get function for the different type of arrays. Also the same goes for the set functions, which are all the same except for the different width of variables they operate on. And all these functions perform a check on the length of the array before operating on their content. Then we have just a utility function, /line. Then we have a global variable which stores the array of the program. The program can work with at most 10 arrays. The list arrays prints the type and length of the defined arrays. If they are null, they are just skipped. The init function receives an ID, a type, and the length. Then it checks that the type is one of the 4 available, which are 8, 16, 32, and 64. Then the ID is checked. If the array is not null, this means that we are trying to define an array which already exists, so it returns. Otherwise, we allocate the memory for the array structure, and then we set the length, the type of this array. Then we compute the size, which is based on the type and the length. So we just divide by 8 because the type is expressed in bits, so we have to divide by 8. And then this size of memory is allocated and pointed by data. This memory is set to 0, and then the pointer to data is stored in the array. Finally, we have a switch statement which, depending on the type of the array, sets the function pointers to the appropriate implementation of the get and set functions. And in the end, the array is stored in the global variable we saw before. And the last function is the delete, which simply receives an ID, and if there is an array, it will free First the backing store buffer, then the array, and then set the pointer to null. And that's all. That's pretty much what the program does. I don't know if you already spotted the bug. Probably these function pointers could be interesting targets for exploration, but we need the bug first. So let me show you in a cleaner way where the bug lies and how to exploit it. The arrays will be stored in the heap since their memory is allocated using malloc. So in the heap we're gonna have a first chunk for the structure itself, and then a second chunk for the backing store. So let's keep this in mind while we have a look at the bug, which lies in the init function. This function receives arbitrary parameters from the user, and then it performs some checks. For example, the ID should be a valid letter and the type can be only 8, 16, 32 or 64, while length can have any value. So this means that when we compute the size, an integer overflow is possible, leading to a wrong amount of memory allocated for the backing store, which means an out-of-bound read-write primitive. So now upon this primitive we can build an arbitrary read and write. Let's see how. First we allocate an array which exploits the integer overflow, followed by another array which is normal. Then we set a value in this second array to be able to identify this array in memory, and then we use our out-of-bound reading capabilities to find this value in memory. This means that now we are able to address the second array from the first one with an index which is stored in bbase in our exploit. This means that we can overwrite data pointer to everything we want, and this is achievable with the set called on the first array. Then we can combine this with the get on the second array to get an arbitrary read, or a set to get an arbitrary write. Now with these two primitives we can build our exploit, which will simply leak two addresses from libc to identify the correct libc and defeat a SLR, and then we're gonna pop a shell. First we leak the address of printf, for instance, then we leak another address from libc, so we're able to identify libc. Then we overwrite the length field of the second array, that field, and then we trigger the call to this function pointer with a call to get, which will effectively call system binsh, giving us a shell. Now let's see if this actually works. So here is the exploit. At first we have the definition of these three utility functions, which are int, get and set. Then we have the get arbitrary read and write primitive, which is exactly the same we saw in the slides. Then we have the read and write definitions with the combination of set get for the read and set set for the write. Then the leak libc, which uses the arbitrary read to leak two addresses from libc, with this you could identify the libc, but since I'm playing on my local machine, I just hard-coded the right one. Then, based on the leak, we also set the base address of libc. And finally, we have the pop shell function, which prepares the argument. It overrides the function pointer and it simply triggers the call to the function pointer. That's all. Same story, usual steps that we saw, and it works.